Thank you, Rod, for the opportunity to address the podium. I'll focus more, I'll make a more technology-oriented talk. I'd like to address the field of driving assistance, advanced driving assistance systems, talk about how it is shaping today and how it would look in small increments into the near future and into the longer future, the big leaps that need to be made in order to go to automated driving. And then I'll talk about some hardware concepts that are necessary in order to support this big software capability growth. As Rod said, we are in the business of artificial intelligence, more specifically computer vision. Computer vision is the science of making computers see and understand what they see. We are a tier 2 in the market. We sell software and microprocessor system on chip that we developed that we called IQ3. We are now in the third generation. Fourth generation chip will be coming out end of this year, and I'll talk a bit about those hardware generations. So let me start about there are two big trends in driving assist. One is an evolutionary trend where active safety technology, which are sensors that are capable of avoiding collisions by applying brakes. This is called autonomous electronic emergency braking, AEBs. And these are coming out in very large volumes, and regulators are putting their weight in terms of incentivizing with star ratings such that by 2018-19, more or less this time frame, almost every new car would have such a sensor. And the camera is a critical sensor in this configuration of capabilities. The second trend is revolution, the ability to transform the way we drive, and this is through automated driving, and I'll talk about both of them. So I'll start with how things look today. So first I'll show a small clip that shows what our system does by overlaying the system detections, the interpretation of the system onto the video. So I'll run this video and I'll stop it and I'll explain. So if I run this video a bit, and let's stop it here, what we see here, we see the system is detecting the green bounding box, the bounding boxes on vehicles. You see bounding boxes on pedestrians. You see a bounding box on traffic sign. You see farther ahead on the right, a bounding box on traffic light. You see a green line on the lane mark. And you see also the pedestrians, even those on the side are being detected, also those that are partially occluded. Let's give it a bit more. You see now the traffic sign on the right, again the traffic light far ahead. You see the side of the car, it's a car, the side of the car also being detected. You see a partially occluded pedestrian on the left. Let's give it a bit more. So what the system does is tries to interpret the visual field at very high details. And this kind of details is sufficient for today's driving assistance systems, for today's functionality, which are based on avoiding collisions, are not yet sufficient for automated driving, and I'll say what is needed in order to go for automated driving. But you see, as it is today, the kind of interpretations are very, very detailed. There's a lot going on here in terms of understanding the scene, pedestrians, vehicles, traffic signs, lane marks, all of this running together at about 30 frames per second. In this case, 36 frames per second. In terms of, and I'll spend 2-3 slides just on where we are. This is we started launching our technology, which is our system on chip and software, since 2007. And what I show here is wherever we were worldwide first in our launches. So in 2007, we launched the first camera radar fusion system on Volvo. 2008, we launched the first worldwide traffic sign recognition. It was on the BMW 7 Series. In 2010, we launched the first pedestrian detection system on Volvo S60, and later on all the platforms of Volvo. In 2011, the first camera forward collision warning, camera-only forward collision warning, without using a radar. 2013, the first camera adaptive cruise control, the first camera traffic jam assist, the first camera partial braking AEB. And in 2015, we're launching Starting with Audi in a few weeks, we're launching the first camera-only full braking AEB functionality on an IQ3. So these are the launches that we're having in 2015 alone. There are going to be 2 IQ3 launches with 8 car manufacturers. We're launching the first worldwide full braking monocular. Monocular means a single camera AEB. This is with Audi. The first worldwide animals detection. So in addition to detecting people, detecting cars, trucks, motorcycles, bicycles, cyclists, also large animals like moose or deer. They're going to be, this will be with Volvo, again, a few weeks from now. The first US-based traffic light detection. It's going to be with a car manufacturer around middle of 2015. First worldwide pedestrian detection at night. So far, all pedestrian detections on the market are daytime pedestrian detection. First time it will run at nighttime will be around middle 2015. And these launches are with our Tier 1 partners, Delphi, Costal, Magna, Mando in Korea, Tier W, and also Tesla. With Tesla, they are acting as their own Tier 1, so we work directly with Tesla. What we see here is that there is a certain camera disruption. Means the functional territory taken by the camera is rapidly increasing. What does that mean? In 2011, the camera, as a single standalone sensor, was taking the territory of the radar in terms of warning against collision. The car would give an alert before an imminent collision, a function that in the past was done by a radar. 2013, ACC, adaptive cruise control, the first time that the camera is doing adaptive cruise control. This used to be done by a radar. Partial braking, AEB, and also traffic jam assist. In 2015, the first launch we're having with Audi in a couple of weeks, it will be full brake AEB. So what we see here is that the camera is gradually taking over functions that historically were done by radars. And the question is why? Why is this happening? So first, the camera is the richest source of raw data about the scene. It's the only sensor that can reflect the true complexity of the scene. It's the lowest cost sensor. Nothing can beat it. A camera sensor costs a few dollars. That's it. All the rest is computing hardware. Every sensor needs computing hardware. So when we talk about the camera sensor, it's simply the camera imager, which is a few dollars. That's it. There's nothing else that can beat it in terms of cost. And cameras are getting better. They're getting better in terms of dynamic range, and they're getting better in terms of resolution. Okay. There are 2 points that need to be, one needs to carefully look at. When you have such a system that apply the brakes before a collision, there are 2 dimensions to problems. One dimension is called the false negative. The car should have applied the brakes, but it didn't apply the brakes. And the other one is false positive. The car should not have applied the brakes, and the car brakes. So the false negative, if you have a system with lots of false negatives, you can compromise the star ratings because these systems, they undergo testing in test track, but they undergo rigid testing. And if your system has lots of false negative, it will not pass the testing. And it will compromise the reputation when tested in the wild, not only by the official testing agencies, but other clubs like ADAC in Germany and so forth. False positive is a much bigger problem. False positive is a catastrophe. You are driving leisurely along a road and all of a sudden your car brakes without any explanation why it brakes. This is a reason for a recall. And this is something which is very difficult to test. You cannot test it on a test track. You need to run it over lots and lots of data to validate that your system indeed doesn't have a false positive. This is an example of recalls on systems that have been recalled in the past couple of years. It is a big problem, recalled on false positives. The point that I'm making here, it is difficult to mitigate functional weakness using clever human-machine interface because the car brakes. You know, if you are talking about alerts, you can have all sorts of clever HMIs to kind of hide weaknesses of your system. But when your car brakes, it brakes. You cannot hide this kind of weakness of a false positive. Therefore, you need very, very high quality software. And one of Mobileye's advantage, since we work with 21 car manufacturers to date, with each car manufacturer, we have hundreds of thousands of kilometers driven. Over 30 product launches that we had to date. We have more than 10 million miles of data recorded. There's no other player in the field that comes even close to such amount of data. So we use all this data in order to validate the system and to make sure that the system will not have these kinds of problems, especially the false positive problem. Okay, so now let's go into the future. That was the present. Let's go into the future, and we're talking about, we'll talk about in two steps. One is the incremental growth. What are the additional functions that are natural to think about when you look into the future? And I have here a long list. Let me show you a few of them. So this is animal detection, going to be launched in Volvo in a few weeks. You can see here that there's a big animal. The system puts a bounding box, and if there will be a collision, the car would brake before a collision. This is another cool feature, which is the ability to reconstruct the shape of the road, to detect potholes and to detect bumps, and actuate accordingly. Actuation could be to ride smoother on the bump, or to brake before a small debris. Our technology can detect the shape of a pothole or a bump to an accuracy of millimeters. The clip that I show here is kind of a test track clip where we're going over a 4 centimeter bump, and you see here the profile which goes up when the car is about to enter into the bump, and then the car control systems make sure that you pass through the bump in a very smooth manner. One way of using this technology is to identify debris. Debris is a 10 centimeter object about 40, 50 meters away, and the goal is even to detect it even more than 50 meters away. Why you want to detect debris? Imagine in the context of automated driving, where you're not holding the steering wheel, you are texting or doing something similar, and there's somebody threw a tire on the road. So it's a small object, 10 centimeter height object, far away. If you hit it, you may flip. So you want your car to know about it, at least warn you that you're going to hit a debris. So detecting debris is a critical element in the context of automated driving, and our system can detect debris. You can see that when it finds the debris, all these blue dots become red, and you see here very, very small objects. So small objects of 10 centimeter size can be detected. Traffic sign recognition. Until 2014, our system would detect 40 different traffic signs over 25 countries, starting from the IQ3 launches that were done 2 months ago with Tesla. It's 250 traffic signs over 50 countries, and by the end of this year, there will be about 1,000 different traffic signs over 100 countries. So this is a big growth in the capability of knowing about all the traffic signs in the scene. Traffic lights. What you see here is that the system will detect the traffic lights in very complex and cluttered scenes. So detecting traffic signs means detecting the traffic signs, knowing also the relevancy, which traffic light is relevant to what direction, also detecting the stop line and stopping at the right point if the car is first in line. And this kind of technology will be already launched this year, 2015. Let's now look at what is needed for automated driving. What I've shown so far are functional growth that is natural, makes sense. You have a system that detects traffic signs, why not detect also traffic lights? You have a system that detects pedestrians and cars, why not detect big animals? You have a system with the ability to reconstruct the shape of the road, why not detect debris or detect bumps and use a feedback loop in order to pass smoother on the bump. So all these are kind of natural growth. You detect 250 traffic signs, why not detect 1,000 traffic signs? But when we go to automated driving, there are additional jumps that need to be made, which are not incremental, and require some new thinking about how to approach the visual interpretation task. So there are two schools of thought. There are two ends of the extreme of how you approach automated driving. One is the store and the line, and the other one is sense and understand. Store and the line means that through a pre-drive, you store a huge amount of data around you, And later, when you do the real-time driving, you match the sensory data that your sensors give you to the stored data. And if the data that you had collected is rich enough, you don't need to do much sensing. This is, in the extreme case, this is Google's approach. Sense and understand, on the other side of the extreme, you record nothing. You use your cameras, you use your radars, you use your lidars, you use your sensors in order to interpret the visual field, just like us human drivers, and use that in order to do the actuation, in order to determine how to drive. So if I put it on a graph, you see here the two ends of the extreme. On the left hand side, it's pre-drive recording, 3D recording, 360-degree surround for every centimeter on the road. Huge amount of data, talking about hundreds of gigabytes to record a city, for example. On the right-hand side of the graph, no recording at all, only sensing. Now, in between, for example, on the left-hand side, there is HD maps, high-definition maps. These are maps that map makers like Navtec, which today is called Here, or TomTom, are kind of building or thinking to build, where, for example, you would know where the curb is at an accuracy of centimeters from you. So have a lot of information that does not exist today, and these are called high-definition maps. So it's not full 3D surround like what Google records, but it's a big jump from today's map to HD maps. And you can think of less intensive recordings, which we call sparse recording. So we are on the right-hand side of this graph, moving left. We will do some recording, but very sparse recording. We're talking about 1 megabyte of data for 1 hour of driving. So very, very sparse recording. Everyone is placed somewhere along this graph. Most of the car industry is on the right-hand side of the graph. Now, when you think about sense and understand, there are several challenges. For example, consider lane marks. You want to determine where to drive, the path to drive. So theoretically, it's quite simple. You detect the lanes. Once you have detected the lanes, you can figure out, the shape of the lane, say a second or third degree polynomial, and this tells you how to drive. But there are many places in the world. Now, unlike Germany, in Germany it will work perfectly, right? But think about Detroit. You would look at an image, you don't see any lanes, and if you see, these are not the true lanes. California, where they have all these box dots. Israel, some of the roads are very crappy. So in many situations, you look at the image and you don't see lanes. But the human driver has no problem in determining the path, because the human driver takes holistic information, looks at barriers, look at guardrails, look at how other cars are driving. There are lots of holistic cues in the scene that tells you how to drive, how to determine the path, not only the lane marks. When the lane marks exist, this is the perfect cue. But even when they don't exist, you can determine how to drive. So this is one big challenge, because you want automated driving to work everywhere, not only on perfect roads. Second is where not to drive. Where not to drive is there a barrier on my left-hand side or right-hand side? Is there a guardrail? Is there a curb? And so forth. So it's not only the objects in my path, but everything around me. So I need to know where not to drive. This is called free space estimation. So there are two big challenges. One, environmental model. Environmental model is ultimately tell me for every pixel in the image what category it comes from. Is this pixel coming from a guardrail? Is it coming from a barrier? Is it coming from a curb? Is it coming from a pedestrian? Is it coming from a car? Is it coming from a truck? A side of the car? Traffic sign? Etc., etc., etc. For every pixel in the image, tell me where it comes, in order that I can build this environmental model, that I can determine the free space, determine where I can drive, where I cannot drive. The second thing is path planning. What I mentioned before. Tell me where to drive. Even when there are no lane marks, tell me where to drive. And these are what we call the problems of tomorrow. And we have been working on these problems for the last 2 years, and they're going to be launched quite soon. I'll mention this in a moment. So the tool that we're using a new tool. It's called deep learning. Again, we are working on it for the past 2 years. What I'm showing here are two sketches from academic research. On the top-hand side, this is called AlexNet 2012. It's one of the academic papers that created a lot of impact on deep learning. So deep learning means that you have a network comprised of layers, where the first layer, the input layer, accepts the image, and then you have a sequence of simple operations, convolution, but many of them, layer after layer after layer, until you reach the output layer, which in the academic research mostly is what is the category of the image. On the bottom side, you see a deep network for face recognition. It is a deep network that achieved human perception level in terms of face recognition. So these deep networks, when they work very, very well. And we decided 2 years ago to start integrating the concepts and the ideas into our methodology in order not to solve the problems that we have solved in the past, like pedestrian detection, vehicle detection, but to solve the problems of tomorrow, the two issues that I mentioned, environmental modeling and path planning, and also the growth of many other objects. I put here on the right-hand side, on the AlexNet, it has 60 million parameters and 832 million multiply accumulate operations. This is huge. There's no microprocessor that can run something like this in real time. So remember this 832 million operations, because later when I'll talk about hardware, we'll see this number popping up again. So the deep learning architecture published in academia, they require hundreds of millions of parameters. And it is very challenging for real-time processing on embedded platforms. And the research on pixel-level labeling, what I mentioned for the environmental modeling, for every pixel, tell me what category it is. In academia, it's very, very sketchy. There isn't any huge success there, and it's definitely not real-time driven. So we developed deep layered architectures for our software, together with additional components, for example, spatial coupling through graphical models, that are designed for IQ3 and IQ4 architectures. For example, on the IQ3, it takes only 5% of the chip, 5% of the capacity of the chip, running at 36 frames per second. So it's very, very efficient. On the IQ4, it will take 0.3%. So we're not talking about something that takes the entire capacity of the chip, something very, very efficient. And these networks are responsible for pixel labeling, for every pixel and the image, tell me what it is, for path planning, for general objects, for the growth into 1,000 different traffic signs and more. So let me show you some examples. I'll go over clips. So the first few clips are the path planning from holistic Q. So I'll show you clips where even if you understand nothing about computer vision, image processing, you'll clearly see you don't see lanes in the image. Of course, I'll show you a clip, not only an image. You don't see any lanes, and determining the path is really challenging if you're going through detecting lanes and from lanes determining the path. So let's look at this clip. So what you see here, the green line is the path determined by the network. There is no lane detection technology today that can handle something like this. There are simply no lanes here. Okay? Let's look at this one here. Because of the shadows and so forth. On the right-hand side, maybe you can see a lane. On the left-hand side, it's very, very problematic for lane detection-based technology. Let's look here. This is a two-way road. On the left-hand side, there's simply no lane. On the right-hand side, there is a road edge. Maybe on the road edge, you can put a lane mark, but on the left-hand side, it's very, very tricky. Yet we are able to handle this quite nicely. Now we can do also tight curves. It's not only straight lines. Nighttime, simply you don't see any lanes here because of the reflections from the lights, from the oncoming cars. The road is wet, therefore the reflections are very, very strong. You hardly see any lanes. Urban traffic. There's no lanes in this road. Yet a human driver can determine the path, and we also can determine the path. Now let's go into this environmental model. What I'm showing here, we're coloring here 3 labels. We're coloring the road in green, we're coloring the rear and front of the car in blue, and the side of the car in purple, and this is for every pixel. Let's have it running. So see that the red line is on the curb. Once there is a curb, and then when the curb disappears, the red line goes to the other side of the curb. And now you can see the blue and the purple lines, the sidecars and the front or rear. And this is a challenging situation. We're going into a tunnel. The light is very bad. So here, there is no specific object detection going on. Is the network learned for every pixel to determine whether it's a road, whether it's a car side, or a car front or rear. Let me show you a bit more. Let's look here. So the green here is very important because the green tells me where is the free space. Okay? Imagine that, first thing that I want to know when I'm doing automated driving is where is the free space. Okay? So look at the green, and also once I determine the free space, the boundary of the free space tells me what is on the boundary. Is the boundary a guardrail, a barrier, a car, a pedestrian, and so forth. Okay? And this is running at 36 frames per second and occupying about 5% of the chip. Here is also a challenging road. You see that, even when we are training this, just tell me where the road is, it knows about cars and other things that are not road. It does not get confused on objects that are not road. So here, where just this blanket is only tell me where the road is. For example, here, there is a curb. This is why it's not going inside. Later, you'll see a pedestrian with a cart, and again, it's not confused, and it's not, the blanket is not going over the pedestrian. Or let's say a bicycle is coming in here, and you can see that the blanket doesn't engulf the cyclist, even though the network was not trained on cyclists in this case. We also detect pavement markings like the arrows. This is also part of road understanding. So it's not only traffic signs, traffic lights, but also all the possible. There are about 15 different pave markings that the system is trained for. Now, if you put everything together, remember that first clip that I showed you. Now it is together with everything, with the blanket, with the detections. So now the system knows where the free space is, where all the objects in the scene are, and in that way we get this environmental model to enable to do hands-free driving. Now, if you put all of this together, we have infrastructure that takes, as an input on the left-hand side, takes an image. It takes flow information from motion. If we have more than one camera, we take also depth information. We take coupling constraints in order to do spatial constraints using a graphical model. We have ego motion fed inside. We have motion segmentation fed inside. Then we have a deep network together with a graphical model that produces on the right-hand side the pixel labeling, the path planning, and objects. We're talking about vehicles, rear, side, a type of object, whether it's a car, an SUV, a truck, bus, and so forth. We don't have police cars, but nobody asks us to do that. Pedestrians, 1,000 traffic signs, traffic lights, pavement markings. We're talking about 1,200 different categories that we are running. And when all of this is coming out? This year. So I'm not talking about something very futuristic. Around middle towards third quarter of 2015, a car manufacturer is going to have this kind of technology running on the car on our chips. Okay? So it's not very, very futuristic. So let's talk about the hardware to support all of this. So our third generation chip launched 2 months ago on Tesla and going to be launched 2 weeks from now with Audi and Volvo, and 9 launches throughout 2015. It has 8 cores, it's 4 CPUs and 4 vector accelerators that are very powerful and are dedicated to computer vision type of processing. That means this kind of chip would not be a chip that will put on a tablet, will not put it on a PC. It will not do video playback, encoding, decoding. It's not designed for this. It's designed for computer vision. Now, last week at the CES, the CEO of NVIDIA showed this card. This is the ZFast card, going to be PCB, going to be launched with Audi around 2016, 2017. It has 2 Tegra X1 chips, as you see there. And there was a big show of computer vision technologies, pedestrian detection, vehicle detection, the kinds of things that we have been doing for many years. And all of this is very, very nice. But what has not been told to the audience that this card has an IQ3 here. And all what has been shown is done by the IQ3. The X1 does what it's designed for. Video playback, coding, encoding, and some yet to be determined parking assist functionalities. The X1 was positioned as a supercomputer, and this is something we never thought about, positioning chips as a supercomputer. So we did some analysis. So let's now compare the X1 to the IQ3 in the context of deep networks. So what you have here is the normal stuff that you see when somebody talks about the chip. It's the clock speed, the number of cores, and the number of multiply accumulate, which is the basic element in computing, multiply accumulate per core. So the Tegra X1 has a clock cycle of 1 gigahertz, has 256 GPU cores, Maxwell GPU cores, and each core has 2 multiply accumulate operations. The IQ3 runs at half the clock speed, 500 megahertz, half gigahertz, has 4 cores, 4 vector accelerators. I'm focusing only on the vector accelerators. And each core does 64 multiply accumulate operations. So on paper, what you need is to simply multiply the numbers. So 1 gigahertz multiplied by 256 multiplied by 2, it's 512 million multiply accumulates per second, which is 1 teraflop, because multiply accumulate is 2 flops. So this is the 1 teraflop that has been announced. The IQ3 on paper has 1/4 of it. It's 128 million megaflops. Multiply accumulate. But what people don't tell you is utilization. What part of this hardware is available at any given time, and this depends on the application that you're running. So if we are running a deep network, one can very easily determine what is the utilization of the Tegra X1, because these cores are available in graphic cards by NVIDIA. The GTX 980 has 2048 Maxwell cores. NVIDIA has published code to run deep networks. It's called CUDNN. And assumingly, this is the most efficient code to run deep networks using using GPUs. So one can use it and measure what is the utilization. You run a network, you know exactly how many multiply accumulate there are, and then you measure what is the utilization. So you see that the Tegra has 0.28 utilization, whereas the IQ3 has 0.8. And that's not surprising, because the Tegra is a general purpose chip, and we are designed for computer vision. So now if you multiply, you get that the effective number of multiply accumulate on the Tegra is 143 million multiply accumulate, whereas the IQ3 has about 100. So there's a 40% difference. But now let's look at the trade-off. Power. Our chip runs at 2.5 watts, Tegra X1 10 watts. 10 watts in automotive is bad. Okay? Silicon area. Silicon area, we can measure the silicon area on the K1. K1 has 192 GPU cores. It's supposed to be very, very similar in size. So the K1 run at 28 nanometer process is 126 millimeter square area. Ours is 42. So there's a factor of 3. But we are on a 40 nanometer process. 40 nanometer process compared to 28 is half. It's 0.7 square. So if we would manufacture our chip at 28 nanometer, it would take only 20 millimeters square. So there's a factor of 6. So we're talking about a factor of 6 in terms of silicon density, a factor of 3 in terms of silicon size. That means its cost here is relevant, and a factor of 4 in terms of power, and there is a 40% difference. So the IQ3 is not far away. Let's look at IQ4. IQ4 is our next generation chip, coming out in October this year, the engineering samples. It has 4 CPUs. It has 3 types of vector accelerators. They come with the VMP is what the IQ3 had, but there are 2 additional ones called PMA and MPC, and they cover the entire spectrum of flexibility versus performance power. And the VMP has 6 cores, 76 multiply accumulated per core, etc., etc. The total, if you multiply everything with the clock speed, You have 1.25 million multiply accumulate, which is 2.5 teraflops, which is 2.5 times the X1, but given the utilization, which is much, much higher, this could be even 10 times more than the X1 for the computer vision processing. So if we're talking about supercomputers, I think our chips, meet the criteria. We never thought about positioning them as supercomputers, but if we talk about supercomputers, it could fit. In terms of hardware, we are promoting what we call a trifocal arrangement of cameras to handle automated driving. So trifocal means that you need more field of view to handle automated driving than normal ADAS. Because you want to see 180 degrees in order to see a very, very tight cut-ins, to see a traffic light when you're first in line, when it's above, to see a cyclist that could jump in when you're in city traffic. You want to see very narrow in order to see those debris very far away. You want to see the debris 80 meters ahead in order to give a driver a chance to do something when the automated car sees a tire on the road. And this is here in a clip showing on the left-hand side, this is the normal field of view. On the right-hand side, this is 150 degrees field of view. And you can see the pedestrians on the side that you simply don't see them in the normal field of view. And with a wide field of view, you can see them. So this trifocal arrangement is one of the arrangements that we promote in the industry for automated driving. And we have a number of production programs going ahead and many more pre-development programs with car manufacturers. Okay. So the way we see, and this is the last slide, the way we see the automated driving going on is that the 2015-16 timeframe is highway autopiloting using the kind of technologies that we have shown. In 2017-18, it will go into city traffic. And then later, once there is a car-to-car communication and more detailed maps would be there, one can even imagine truly autonomous driving where the driver is completely out of the loop. So to summarize, ADAS is to be dominated by cameras. It's not only me saying it, others are also saying it. The primary sensor for automated driver would also be dominated by cameras, multiple cameras, and radars and lidars would be used for redundancy and for additional robustness when cost allows. Visual interpretation is difficult if done at high quality. Doing something at low quality is easy. One can show demonstration quite easily, but high quality is tough. Requires huge validation data over multiple geographies and OEMs. And automated driving, the two building blocks that are required above ADAS are environmental modeling and path planning, which in turn require kind of leapfrog technological jump. Thank you.
Thank you.